In 1935, Albert Einstein wrote a letter calling a new scientific theory absurd, dangerous, and, quote, spooky. That theory turned out to be correct. It's called quantum mechanics, and nearly a century later it has led some of the most rational, evidence-driven people on Earth to a conclusion so strange that many of them refuse to say it out loud, that reality, as you experience it, might not exist without you. Let that sink in for a moment. Not exist, not blurry, not uncertain, simply absent, undefined, unwritten, until the instant something or someone looks. This isn't the plot of a science fiction film. It isn't a thought experiment dreamed up by a philosopher with too much free time. It is the working, tested, mathematically verified backbone of modern physics. The same physics that gave us lasers, computer chips, MRI machines, and the GPS satellite guiding you home tonight. And somewhere buried inside all of that undeniable success is a mystery so deep that it has quietly terrified some of the sharpest minds in scientific history. To understand why, we have to go back to a single, deceptively simple experiment. Imagine a wall with two narrow slits cut into it, and behind that wall, a screen that records where particles land. Fire a stream of tiny particles, electrons, photons, whatever you like, one at a time, toward those two slits. If particles behaved the way common sense tells us they should, each one would pass through one slit or the other, like a marble falling through a hole, and you'd end up with two neat piles on the screen behind, one for each slit. That's what a reasonable universe would produce. That is not what happens. Instead, the particles land in a pattern of alternating bright and dark bands, a pattern you only get when waves interfere with each other, canceling out in some places and reinforcing in others. It's the same pattern you'd see if you dropped two stones into a still pond and watched the ripples cross. Except here, there's only one particle at a time. There's nothing for it to interfere with, unless, somehow, each individual particle is passing through both slits simultaneously, interfering with itself, existing in two places at once until it strikes the screen and becomes a single point. That alone should stop you in your tracks. But the story gets stranger. If you place a detector at the slits, a device simply designed to observe which slit each particle actually goes through, the interference pattern vanishes instantly. The particles stop behaving like waves smeared across two paths, and start behaving like the marbles common sense expected all along, landing in two clean piles. The mere act of looking, of gathering information about which path was taken, appears to force the particle to commit to a single, definite reality. Physicists call this the observer effect, and it is one of the most misunderstood ideas in all of science, partly because it sounds like something mystical is happening, and partly because, in a very real sense, something mystical does seem to be happening. To be clear, this isn't about human consciousness staring at a particle and willing it into existence through sheer thought. The detector doesn't need a person watching a screen in real time. It simply needs to interact with the particle in a way that records, even in principle, which path it took. That distinction matters enormously, and we'll come back to it. But even stripped of any mystical flavor, the core fact remains bizarre almost beyond words. Somehow, the universe behaves differently depending on whether information about a system exists somewhere, anywhere in the world. This single experiment, the double-slit experiment, has been called the central mystery of quantum mechanics, and it has been run again and again for over a century, with electrons, with photons, with atoms, and even, astonishingly, with large molecules made of hundreds of atoms. Every single time, the same eerie pattern holds. Particles behave like waves of possibility when nothing is watching, and like solid, located objects, the instant that possibility is measured. Niels Bohr, the Danish physicist who became one of the chief architects of quantum theory, embraced this strangeness. He argued that before measurement, a quantum system simply doesn't possess definite properties at all. It isn't that the particle is in one place and we don't know which. It's that the particle has no single location, no single state, until an act of measurement forces one to emerge. This became known as the Copenhagen interpretation, named for the city where Bohr worked, and for decades it has functioned as the closest thing quantum physics has to an official party line. Reality, according to Copenhagen, is not something that sits there waiting to be discovered. Reality is something that gets created, moment by moment, through the act of observation itself. Albert Einstein hated this idea with an intensity that shaped the rest of his career. He had, ironically, helped lay the foundations of quantum theory himself, but he could never accept that the universe had no definite properties until someone looked at it. He believed there had to be some deeper hidden layer of reality, some set of facts the theory simply hadn't uncovered yet, that would restore the common sense picture of a world that exists independently of any observer. It was in this spirit that Einstein and two colleagues devised what became known as the EPR paradox, named for Einstein, Podolsky, and Rosen, an argument designed to prove that quantum mechanics, as it stood, had to be an incomplete description of reality. The EPR argument relied on a phenomenon that Einstein found so unsettling he refused to accept it as physically real. Two particles can become entangled, linked in such a way that measuring a property of one instantly tells you the corresponding property of the other, no matter how far apart they are. Not a fraction of a second later, not limited by the speed of light, instantly. Measure one particle in a lab on Earth, and its entangled partner, even if it were sitting on the far side of the galaxy, would immediately reflect a correlated outcome. Einstein called this spooky action at a distance, and he considered it so absurd that he used it as evidence that quantum mechanics must be missing something, some hidden variable, some secret set of instructions each particle carried with it from the moment they separated, that would explain the correlation without requiring any strange, instantaneous influence. For nearly 3 decades, this remained a philosophical standoff. Both sides had compelling arguments, but no one had a way to test which picture of reality was actually correct. Then, in 1964, a physicist named John Stuart Bell found a way to turn the philosophical dispute into an experiment. He derived a mathematical inequality, now known as Bell's theorem, that any theory based on hidden, predetermined variables, the kind Einstein wanted, would have to obey. Quantum mechanics, on the other hand, predicted that this inequality would be violated. It was, in effect, a referee's whistle waiting to be blown. Whichever way nature actually behaved, the experiment would reveal it. Starting in the 1970s and accelerating through the 80s, 90s, and into the 21st century, physicists built increasingly sophisticated versions of this test. Alain Aspect in France, and later Anton Zeilinger and John Clauser, working independently, closed loophole after loophole that skeptics had raised, tightening the experimental conditions until there was almost no room left for a conventional, hidden variable explanation to survive. The result, confirmed again and again with extraordinary precision, was unambiguous. Bell's inequality was violated. Einstein was wrong. There is no hidden layer of local, predetermined information that particles carry with them. The correlations really are as strange as quantum mechanics predicted, and in 2022, Aspect, Clauser, and Zeilinger were awarded the Nobel Prize in Physics for proving it beyond reasonable doubt. This is where the story stops being a historical curiosity and starts becoming genuinely disturbing, even to people who have spent their entire careers inside this field. Because what Bell's theorem and its experimental confirmation actually rule out is not some minor technical detail. They rule out an entire intuitive picture of the universe, the picture in which objects have definite properties, whether or not anyone is measuring them, and in which nothing can influence anything else faster than the speed of light. Quantum mechanics forces you to give up at least one of those two assumptions. Either particles genuinely don't have definite properties until measured, or there is some kind of influence that can act instantaneously across any distance, violating what Einstein considered one of the most sacred principles in all of physics. Physicists have spent the better part of a century trying to find a comfortable way to live with this. None of the available options are comfortable. One option, favored by many working physicists, simply because it lets them get on with calculations without existential vertigo, is to treat quantum mechanics as a tool for predicting the outcomes of measurements, and to refuse to ask what's really happening underneath. This pragmatic stance says, the equations work, they predict experimental results with staggering accuracy, stop asking what it all means. But this approach, sometimes summarized by the phrase, shut up and calculate, has always felt to many people like a retreat rather than an answer. It tells you how to use the theory. It doesn't tell you what reality actually is while no one's looking. A second option takes Bohr's original position and pushes it to its logical extreme. If a quantum system genuinely has no definite state until measured, then, in some sense, measurement, or observation, is doing real work in constructing the world. Some physicists, most famously the Hungarian mathematician John von Neumann, and later the physicist Eugene Wigner, took this even further, suggesting that it might ultimately be consciousness itself, the presence of a mind capable of registering an outcome that collapses the range of quantum possibilities into a single, definite actuality. This idea, though captivating, remains deeply controversial, and most physicists today consider it unnecessary and unproven, largely because ordinary physical interactions, with no consciousness involved at all, appear sufficient to explain the same collapse-like behavior. Still, the fact that a serious mathematical physicist of von Neumann's caliber took the consciousness hypothesis seriously tells you something about how far the rabbit hole goes. To feel just how strange this becomes once you scale it up from a single particle to something larger, it helps to revisit one of the most famous thought experiments in the history of science, one that was actually designed as a criticism, a kind of reductio ad absurdum rather than a serious proposal. In 1935, the Austrian physicist Erwin Schrödinger imagined sealing a cat inside a closed steel box, along with a tiny amount of radioactive material, a Geiger counter, a hammer, and a flask of poison gas. If, within a given hour, a single atom of that radioactive material happens to decay, the Geiger counter detects it, triggers the hammer, shatters the flask, and kills the cat. If no atom decays, the cat lives. Radioactive decay is a genuinely quantum event, meaning that until it's measured, the decaying atom exists in a superposition of having decayed and not having decayed, both possibilities layered on top of each other. Follow the logic of Copenhagen all the way through, and something deeply uncomfortable falls out the other end. Since the cat's fate is entirely wired to that quantum event, the cat itself, according to a strict reading of the mathematics, should also exist in a superposition, simultaneously alive and dead until someone opens the box and looks inside. Schrödinger intended this as a kind of reductio ad absurdum, a demonstration that something must be wrong with taking quantum superposition too literally when applied to macroscopic, everyday objects like cats. And yet, nearly a century later, physicists still don't have a universally accepted answer for exactly where or how or why the quantum world of smeared out possibilities gives way to the ordinary world of cats that are simply alive or simply dead, not some eerie combination of both. Decoherence offers a partial, practical answer, explaining why we would never actually observe a superposed cat given how violently and quickly such a large system interacts with its environment, but it doesn't fully settle the deeper philosophical question of whether, underneath that practical explanation, the cat, the box, and everything else in the universe still harbors some residue of that unresolved quantum ambiguity, at least for the briefest, unmeasured instant before observation forces a single outcome to emerge. A third option abandons collapse altogether. In 1957, a young physicist named Hugh Everett III proposed something that sounded, at the time, almost like science fiction. What if the wave function, the mathematical object describing every possible outcome of a quantum event, never actually collapses at all? What if, instead, every single possible outcome happens, but in separate, non-communicating branches of reality? In this view, when a particle passes through two slits, it doesn't choose one path, and it doesn't remain in some hazy, metaphysical limbo either. Reality itself splits. In one branch of existence, the particle went left. In another equally real branch, it went right. Every measurement, every decision point at the quantum level spawns a fresh branching of the universe, and you, the observer, split right along with it, one version of you experiencing each outcome, each version fully convinced they are the only one, each version entirely unaware of the others. This is the many worlds interpretation, and it has, remarkably, gone from a fringe idea dismissed by most of Everett's contemporaries to one of the leading interpretations, taken seriously by working cosmologists and quantum theorists today. It solves the measurement problem elegantly in the sense that it never requires a mysterious collapse at all. Everything simply keeps evolving according to the smooth, deterministic equations of quantum mechanics, with no special role for observers or consciousness whatsoever. But the price of that elegance is almost unimaginably steep. It requires accepting that there are, right now, uncountable numbers of versions of you, of Earth, of every galaxy in the visible universe, each one splitting apart from the others every time a quantum event with multiple outcomes occurs anywhere, which is to say, constantly, everywhere, without pause. There's a fourth path, one that has gained enormous traction among physicists over the past few decades, not because it resolves the deepest philosophical puzzle, but because it explains something crucial about why the everyday world looks so solid and classical despite being built from this strange quantum foundation underneath. It's called decoherence. The basic idea is this: a tiny, isolated quantum system, a single photon or electron in a carefully controlled laboratory, can maintain its delicate superposition, its existence in multiple states at once, for a meaningful stretch of time. But the moment that system starts interacting with its environment, with stray air molecules, with photons of ambient light, with the trillions of particles making up a measuring device, that superposition doesn't so much collapse as it leaks away, spreading out into an unimaginably complex entanglement with everything around it. The interference effects that made the superposition special become, for all practical purposes, undetectable, because you would need to track and recombine an astronomical number of entangled particles to ever see them again. Decoherence explains beautifully why we never see a baseball or cat or person existing in two places at once, even though, in principle, quantum mechanics says nothing should stop it from happening. Large objects are so relentlessly and continuously bombarded by their environment that their quantum weirdness evaporates into the surrounding world almost instantaneously. But here's the catch, and it's the reason decoherence, for all its explanatory power, doesn't actually solve the deepest version of the mystery. Decoherence explains why we don't observe interference between different outcomes. It does not explain why only one of those outcomes ends up being the one we actually experience. In the many worlds picture, decoherence is precisely the mechanism by which the universe branches. All outcomes still happen. They simply become causally isolated from each other. In the Copenhagen picture, something else, some genuine collapse, still has to occur to select a single actual outcome from the branching possibilities. Decoherence tells you why the world looks classical. It doesn't tell you why there's only one classical world that you, specifically, are living inside of. This is the point where the story stops being abstract and starts feeling personal, almost vertiginous. Because if you take these ideas seriously, and an enormous body of experimental evidence says you should, then the solid, continuous, single reality you experience every single day, the chair you're sitting in, the light in the room, the fact that there is exactly one version of this conversation happening, none of that is guaranteed by the fundamental laws of physics in the way you probably assumed it was. At the deepest level currently known to science, the universe deals in possibilities, probabilities, and branching potential, not in fixed, singular facts. The singular, definite world of your daily experience might be something closer to a special case, an emergent illusion built on top of a far stranger and more fluid underlying reality, rather than the fundamental truth of things. Some physicists have pushed this line of thinking even further, into territory that borders on the philosophical vertigo, of asking whether the universe has any objective existence at all when nothing within it is doing the observing. John Wheeler, one of the most influential theoretical physicists of the 20th century and a close collaborator of both Einstein and Bohr, proposed a thought experiment called the delayed choice experiment. In it, the decision of whether to measure which path a particle took can be made after the particle has already, in some sense, passed through the slits. And astonishingly, experiments confirm that this later choice still determines whether interference appears or not, as if the particle's past behavior is being decided retroactively. Wheeler took this so seriously that he proposed what he called the participatory universe, the idea that observers, through the very act of measurement, might play a role in bringing aspects of the past into definite existence. It's an idea that sounds almost too strange to be scientific, and yet it emerges directly from experiments that have been run in real laboratories with real, repeatable, measurable results. It's worth pausing here to address the misconception that inevitably creeps into popular explanations of all this. None of what we've discussed allows for faster-than-light communication, and none of it allows you to consciously will a different outcome into being through willpower or intention. The entangled particle correlations, as strange as they are, can only be discovered by comparing results after the fact, through ordinary, slower-than-light communication, which means no useful information is actually transmitted instantaneously, no matter how spooky the underlying correlation might be. And the observer effect in the double-slit experiment has nothing to do with belief, expectation, or conscious intention. A perfectly unconscious, entirely mechanical detector produces the exact same collapse of the interference pattern as a human being staring at a screen. Whatever is happening, it's about information becoming physically embedded somewhere in the universe, not about minds exerting mystical influence over matter. This is important because a great deal of popular pseudoscientific content has hijacked these genuine mysteries to sell claims about manifesting reality through positive thinking, and that is simply not what the physics says, however tempting that leap might feel. And yet, stripping away the pseudoscience doesn't make the real mystery any less profound. It might make it more so. Because even in its most rigorous, most carefully hedged, most soberly peer-reviewed form, quantum mechanics still tells us something that cuts directly against every intuition evolution ever gave us. It tells us that the universe, at its most fundamental level, is not a stage full of objects with fixed properties, patiently waiting to be discovered. It is something closer to a vast, interconnected web of potential, a landscape of possibilities that only resolves into anything resembling the solid world we know when information about it becomes entangled with the rest of the universe, whether through a measuring device, a conscious mind, or, if the many worlds camp is right, through the endless, silent branching of reality itself into uncountable parallel versions of everything that has ever happened or ever will. This is why so many physicists, when pressed honestly, admit to a kind of quiet unease about the foundations of their own field. Richard Feynman, one of the towering figures of 20th century physics, and a man who used quantum mechanics daily to make some of the most precise predictions in the history of science, famously said that he thought he could safely say that nobody understands quantum mechanics. He didn't mean the mathematics was too hard, he meant something deeper, that no one has ever managed to build a picture of what is actually happening. Underneath the equations, that makes intuitive sense to a human mind, evolved to track spears and predators across an African savanna, not to comprehend particles existing in superposition across branching timelines. Stephen Hawking, for his part, once remarked that he didn't demand a theory correspond to some notion of reality, because he wasn't sure what reality even meant anymore, that all he required of a theory was that it correctly predict the outcomes of experiments. Coming from two of the most celebrated scientific minds of the modern era, these aren't casual throwaway lines. They are candid admissions that, at the deepest level, the nature of reality itself remains genuinely unresolved, not because scientists haven't tried hard enough, but because the universe itself may simply refuse to give a single tidy answer. What makes all of this especially unsettling is that it isn't confined to exotic laboratory conditions or abstract thought experiments anymore. With quantum computers, machines that exploit superposition and entanglement to perform certain calculations at speeds impossible for any conventional computer, are being built right now by companies and governments around the world, explicitly relying on the reality of these strange effects to function at all. Every time a quantum computer successfully completes a calculation that would take a classical machine thousands of years, it is, in effect, an experimental confirmation that the branching, probabilistic, observer-sensitive nature of quantum reality isn't some obscure academic curiosity. It's a functioning piece of engineering, sitting in a research lab, quietly proving that the universe really does behave the way this deeply strange theory says it does. So where does that leave us? Not with an answer, and that, more than anything else, is what unsettles scientists the most. After 100 years of experiments, Nobel Prizes, and some of the finest mathematical minds in human history dedicating entire careers to this single question, there is still no consensus on what is actually happening when a quantum possibility becomes a single observed fact. Does the universe genuinely branch into countless parallel realities every single moment? Does some form of collapse, mysterious and still unexplained, select one outcome from many? And if so, what triggers it? A measuring device, a conscious mind, or something else entirely that no one has thought of yet? Is there a deeper layer of reality still waiting to be discovered, one that would finally satisfy the intuition Einstein refused to abandon, even though every experiment so far has only tightened the case against him? Nobody knows. Not with certainty, not yet. And maybe that's the most honest way to end this. Not with a tidy resolution, but with an invitation to sit inside the discomfort for a moment. The same discomfort that has kept some of history's greatest scientific minds awake at night, wrestling with a universe that refuses to hand over its deepest secret. Every single day you move through a world built out of trillions upon trillions of these tiny, unresolved mysteries, particles flickering between possibilities, information quietly entangling itself across space, decisions about reality being made and unmade faster than thought, all of it stitching together somehow into the single, coherent, breathtakingly ordinary experience of being alive, of reading these words, of existing in exactly one place, at exactly one moment, in exactly one version of reality that you can call your own. Whether that singularity is fundamental or a beautiful illusion sitting atop something far stranger, remains one of the last great open questions in all of science. And perhaps that's not something to fear after all. Perhaps it's the most honest reminder available that the universe, even after everything we've learned, is still far stranger and far more wonderful than common sense ever prepared us to expect.